oh, in blockchain, we only believe in cryptography. In math, we believe in signature. We believe in proof. So that's very crucial. But in some of the solutions, like station and like side chains, in that case, you have to trust entity, no offense, like BSC, like Polygon, and they are trustworthy, I mean. But couldn't we have a better way that is just like Ethereum mainnet? We have to trust the consensus itself. So that is the base differences between layer 2 and other scalability solutions. That is the security is based on Ethereum mainnet. Let's make an example. In traditional information security, you have VPN. In some big companies, you have to connect into your VPN using your credentials and inside the LAN and to access anything. But once you penetrate it or get inside the VPN, basically you are free. Hey, it's database everywhere. You can dump them and do bad things about it. So now there's a new concept called zero trust, which is for every step you've done in the LAN of certain corporation, they have to be audited. That is whether it's read, write, or update, they have to be audited thoroughly. And every step there must be a confirmation. So it is the same in layer 2 and blockchain and so on. Instead of trusting human, trusting some nodes, some validators, there will be some sequencers, watchers. Instead, we want to trust code, trust math, and trust proof, trust hash. So yeah, finally, we are mature enough to have something at least vulnerable layer 2, be it optimistic rollup or DK rollup. And yeah, maybe there is some, of course, a lot of you already knew the future development of Ethereum, but for some of you, there's one critical concept called abstraction in computer science, which is, yeah, credits to EMKYCCTP on Reddit. This one is pretty easy to understand. So abstraction is not something like Picasso's paintings. No, abstraction is that if we have one thing very complex, we just try to make it modularized and separate into a lot of different parts. And between those parts, they just have to follow some standardized procedure. Like in TCP/IP, we have TCP/IP 7 layers or 5 layers, right? And if you are doing applications, you don't have to know how router works. You don't have to know how BGP protocol works. All you have to know is, hey, I have a socket connection. And because all the others underlying mechanisms, they have been abstracted. And it is the same, exactly the same is happening. History is repeating again in a good way. On Ethereum, so yeah, we have data shards, we have consensus layer. By the way, this is the security part, and execution layer. And for consensus, that means in a very simplified way, that means how to produce block, how to determine the sequence of block, what kind of transaction should be included in a block, etc. And for execution, it's all about state transition. I mean, previous state, n-1 state, and a lot of transactions. They want to execute all of those transactions in a certain order, and they got transited to a next state, right? So that is execution. And execution is very, very resource intensive, and that is why Ethereum is now one of the main reasons. So yeah, please look at it. Oh, let me make it bigger. So yeah, bridges, we all know that. We all love bridges, and we all hate bridges because a lot of the, accidents. Yeah, so in alternative L1, some other main chains, or in some side chains, there's only bridges. So we have to trust on the provider of that side chain or that L1 in order to bridge your assets from Ethereum to the side chain. But bridges alone are not ideal. So yeah, let's take a look at this part, roll-ups. So to explain roll-up in a more active way, we are called scroll, right? So when you are doing a scroll, it is like bang, and you roll it up. And instead of it's so big, now it's so small. And roll up is things like that. By taking out some unnecessary parts in the transaction, and the transaction metadata can be a little bit fewer. So yeah, the data storage will be a little bit less of a problem, but it's still a problem. I won't talk about that today is called data bloating. But yeah, check at this and make it bigger. Proof, right? Instead of bridges only, now we have proof. So that is why I talk about information security. Talk about we have to trust math, not people. As long as we have proof, and we are fine, because now the proof can make sure trust no one from the X file. The proof can make sure that no one is say lying or no one is acting mistrust. We don't have to believe on the watcher. There's no more, or at least not any more complex mechanisms for the different kind of contract implementation. So it's zero-knowledge proof only. So it is very cryptic. Even I gotta admit, I'm a applied cryptographer, but even I do not know a lot of the details and nuances in the zero-knowledge proof. So in order to make it simpler for everyone, here's the very, very easy analogy to it. Thanks to Elizabeth Sasson from Starware, his paper is really well written. So outsourcing tax calculation. For example, now it's tax season, we all hate that. And the government is being even more lazier. They are like, hey, Jerry, this is your tax data, but we are too lazy to calculate it for you because we, government, our IT is bad. And I'm like, no, so I have to calculate it myself using my computer. So can I cheat on it? Considering X is something that your government knows, that is your tax data. And X is something I know because it's my tax data. And formula f of X, thinking it's 1 plus 1, 1 times by 1, etc., math formula, equals to Y. Y is the result to the amount of tax that you gotta pay to your country, not your nation, not year. But can we rely on it? Of course, yes. Just like we will do wrong on our math test, we will do wrong on this too, whether we meant to do it or we are acting dishonest. So what's the result? So how do we solve it? So there's a concept called computational integrity proof. That is, we want to make sure using some, math magic. That is, we can make sure, for example, if we were to calculate 3 times by 2, we have to plus 3, that is 6, right? But if we have to count like 3 times by 7, and we have to like plus 3 for 7 times, and each step, one step, 3 plus 3, 6, 6 plus 3, and 3 plus and 9, 9 plus 3, etc. So computational integrity proof is that although no one is watching over me by using some math magic, cryptographic magic, the receiving side can ensure that, hey, I look at your pi. Pi is generated together with this formula. By looking at your pi, I know that, hey, you've done every step correctly. By correctly, we mean that, A, the X is correct because your government has X, right? And I have X, right? So government can use their X, which should be the same as our X, using the same f of X, the formula, and they don't have to calculate themselves. Instead, they just look at pi. You know, there's one thing called trapdoor function. That is when you, okay, let's talk about when RAR. If you have to archive something, it's slow. But if you have to decompress something, it's fast, right? So calculating this is slow, but looking at pi is right. So for government, this computational integrity proof magic can help them, like, they are essentially outsourcing the computation, the hard part, to us. And they have to only to make sure that the pi is correct, provided by X, and Y is correct. And that's all. So the government don't have to worry about, A, their computers are not powerful enough, and B, the proof is easy to verify, so everything is correct. And why were I having this example? Deja vu? Do you recall this one? So the point on Ethereum L1 is that Ethereum L1 is slow due to some technical debt or community debt. So we want to outsource some computation to some other entity. And that is the same situation here. The government wants to outsource their tax calculation to people, but they do, instead of trusting people because people will lie, we don't want to pay taxes, right? But so there has to be a proof, and it is exactly the same in this case. Like we want Rollup to provide proof so that all the state transitions is done correctly and can be verified by everyone. By everyone, I mean everyone, just like you and you and you. We have GitHub, not we. Our community has GitHub open source repos that can make you to verify the Rollup proofs on chain yourself. It's pretty interesting. Yeah, so Squirrel, we call ourselves a scaling solution for Ethereum. We want to make Ethereum faster together with everyone else, every other L2 solutions. And so Squirrel is also an EVM equivalent ZK rollup. So yet another buzzword. Maybe I will not call it buzzword. Yet another hard to understand word. What is EVM equivalent? Yeah. So the point is, I was talking like this is something so easy, but in fact, the f of x, in order to like converting this calculation into something that is that can be fit into zero knowledge proof systems. It's not trivial. It is very hard. And how hard? Let me raise an example. I mean, a lot of you are Build.some participants, right? It is very hard for you to, in order to deal with some very low-end concepts. Like we're all very familiar with high-end languages, but if you were to say write your code in assembly language, what would be like? You'll be like, hey, my head is faulty. So it will be the same thing happening in zero knowledge proof if we were to write those things in circuit. By circuit, that means circuit. Just understand circuit this way. So in zero knowledge proof, you have something you want to prove, be it layer 2, be it transaction data, or be it text calculation. And in order, we want to transform that into something called circuit, so that people, when they are looking at proof, they can run the circuit and to see it is right. So think circuit as the calculation itself. And yeah, the way Circon, like languages like Circon, it is very hard to write this kind of thing because it is prone to error. And you know, people like us, we all prone to error. There's many rug pulls on Ethereum on blockchains all the time. So in software engineering, one thing you have to remember, if some languages it's very hard to make something wrong, like the memory management is bad, or the scope is bad, the scope of the variable is bad, and people will fail. And this is not ideal if we were to write those proofs ourselves as general smart contract engineer. So what to do? Yeah, also having to write a proof for every contract written, it is also annoying because it's hard. So remember abstraction? Yeah, it's abstraction again. So instead of doing anything on the upper layer, can we do anything in the bottom layer so that everything is taken care of? Like in TCP/IP, we don't have to know about the BGP, the routing protocol. We only have to worry about the top layer, right? So in this case, the top layer is smart contract, and in the middle layer, maybe it's gas, so Ethereum, the client, and in the bottom, it is EVM, Ethereum virtual machine, where we execute the state transition. So instead of abstracting the topmost layer, if we were to abstract the bottommost layer, and the hard work should be done by engineers like in Squirrel in Starware, or in DKSync in Aztec, things can be solved, right? So yeah, maybe not that easy, but we have a glimpse of all. So yeah, you see, okay, so the point is what is DKEVM? How do we make a proof? So that for gas, so Ethereum, we have some execution traces. Remember we say like 3 times by 7, we plot it by 7 times, and it is the same in Get. There is execution traces like program counter 1, 2, 3 in assembly languages. And we just grab the traces and try to convert it into the circuit input. By circuit input, I mean f of x equals to y, right? And the x is the circuit input. That is something that we want to prove. And we've done the calculation, feeding input x, and output is y. And so that will be fit into different opcodes in the EVN, like the RAM circuit, event circuit, storage circuit, other circuit. The interaction here is complex, so I'll just keep it at the time. You can check our YouTube channel for more details. And after that, we just aggregate the proof into one big proof. Then it's done. So here is a brief comparison to all of the, maybe not all, sorry, to some of the L2 projects, so on. And you can see that the difference here is the abstraction level is different. I'm not going to attack or say anyone. If I say anything wrong, please, I don't mean to offend anyone. But the point is, if you do abstraction in different level, you got different trade-off. Like if you did the thing like Starnet did, I can assure you that the performance will be very, 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 very good. But in the same time, people have to learn how to write Carol, or people have to learn how can we transpile, how can we convert our code from Solidity to Carol. And that is one thing, that is another engineering feat that has to be done by the excellent people in software or in the community. So yeah, from the left to the right, that means the trade-off in the where in the left, the projects tend to be more efficient and flexible, but in the same time, they are a little bit less, a little bit less EVN equivalent. That means some opcodes may not be supported, or some behaviors might be a little bit different from Ethereum mainnet, and you have to change your code, but they are efficient, right? So from here to here, you can see that the abstraction is happening in the language level, in the compiler level, or in the assembly language level, like in Polygon Hermes, they have assembly in between virtual machine to deal with opcode and their storage status, etc., etc. But in Squirrel and Ethereum, we try to do it the hard way. By hard way, it means that the efficiency may be not so good at the moment, but it will be so good in the future because you can try our testing, by the way, it is already good. So that we aim to make every developer here, that is you and you and you and you don't have to learn anything about Squirrel. You just open your hard hat, open your Foundry, or open Remix ID, which we will do in our booth, and then we just deploy like what you'll be doing on Ethereum, and that's the most ideal situation. So yeah, we are all in a healthy competition, and all we want to do is make Ethereum a better place. Yeah, so summary about today. Hey, we don't want to care too much about contract migration, and Squirrel will do it for us because we abstract the proving part in the underlying layer. And B, you don't have to trust us. By trust, I mean the Squirrel L2 is down someday. You can be damn sure that you can call some emergency exit function in L1 so that everything there is being out, your funds are safe because it's in the layer 1 contract. And 3, for any of the layer 2 solution here, they are all cheaper than mainnet. So yeah, that's the main thing. You are free to experiment and do whatever you like of it. Maybe it was impossible on the mainnet, but now it is possible on layer 2. So yeah, I hope after today you all understand what L2 is and you will not be confused by all the buzzwords. So yeah, thank you. So yeah, maybe 10 more thanks for, okay. Maybe 30 more seconds for you to scroll this, scan this and enter our Telegram. Thank you, Bob, thank you, 1inch for shortening your speech so I get so much time. Sorry and thanks. Yeah, please join us.
Thank you, Zari, for your special speech.